Hello everyone. So I'm Jeremy Belot. I'm in a PhD with under the direction of Laurent Pesquet in the CDSI team. And today I will talk about Bayesian system and especially dedicated circuits to solve Bayesian inference for sensor fusion problems using stochastic representation. So don't worry if you don't understand these terms. I will try to explain them during this presentation. Okay, so today with the rise of AI and the Internet of Things, there are more and more data to be collected, processed, and redistributed on systems that are smaller and smaller, and so there are more and more constraints in energy, and so the sensor fusion might be a solution to tackle this problem. In that it can synthesize all this data near to the sensor and transmit only the pertinent information to the cloud to save precious bandwidth and energy. And so in this context, the Bayesian theory can build an explainable models for the sensor fusion, and it can also overcome the lack of precision of the data. So the Bayes theorem, which is as it follows there, it is used to compute a set of probabilities, a distribution of certain causes from a priori knowledge on these causes and observation compared to a model, so which I called there the likelihood. So it involves two random variables, S, the variable of interest, S for searched, and the variable of observation, K for known. And so when we try to solve this Bayesian inference, we try to compute this Bayes theorem on each discretization of the variable S. So on each cause, and we are looking for the cause that is more likely to have caused the observation that we get. Okay, so apply to a sensor fusion problem. We have this relation. So the probability of my variable of interest S knowing my n sensors is proportional to a prior S multiplied by n likelihoods. And we, as I said, we have to process this relation m time, m being the cardinal of the variable of interest, in order to get the distribution, the wanted distribution. So we have a lot of multiplication to do, n times m, and so a dedicated circuit to solve this Bayesian inference can be based on a multiplication matrix as it follows. So this is my architecture of a circuit dedicated to Bayesian sensor fusion. So we have there all my priors that I have to multiply by all my likelihoods there to get the wanted distribution. I see that there's a. Do you can you hear me? I mean, is there a problem or not?
We can
No, no, okay,
we
sorry.
can hear you, but we see the second slide. Are you still at the second
Yeah,
slide?
sorry, yeah.
Okay, so then it's correct.
Okay, thank you. Um, and so this is my my multiplication matrix trying to solve the distribution, the wanted distribution. And so what I have in output is has to be seen as the degree of trust to be placed in this observation for a certain causes. So in order to better understand what I said, let's apply this system to a known problem, a known sensor fusion problem, the sound source localization. So let's say we have a person in a room, and we have two set of two pairs of mics, of microphones. And so the fact that my microphone are a bit shifted will induce in the time a certain temporal shift delta t, and so in the discrete domain it will induce a sample shift delta n, which will induce in the spectral domain a different phase difference on each frequency fk that we study. Uh, so let's say we study 50 frequency, so 50 phase difference. Since we have two pairs of microphones, we will have 100 of sensors, 100 of observation in our system. And if we divide the room by a grid of 8 by 8, we will have 64 sources. No, not sources. 64 causes. I mean, 64 line in my matrix. So the distribution that we want there is given by the prior, the knowledge a priori that we have on each of the line. If we don't know anything, uh, we put just one divided by 64, a uniform distribution for the priors, and we multiply the prior by the likelihood, so the probability of my each of my difference of phase for each of my cell on the room. And we can see there that the line where the probability is the higher is where where the source is. So we have to interpret it as the source, the sorry, the
متنفر نباشن چرا انتظار دارن مردم همیشه اینا رو دوست داشته
hello, I don't get it. Okay. Um, we have to interpret it as this line is more likely to this cause s equal to s18 is more likely to have caused all this observation that I get, delta phi n. Okay, so now how do we generate the likelihood probability of delta phi knowing s? It is given by my sensors and a certain model. So let's say that we consider that our sensors are not exactly perfect, and they are following a certain probabilistic law. So typically a normal law with a certain standard deviation for each of my sensor kj. The model, our model here, the acoustic model, so a physical model, will give us the mean of the Gaussian. It gives us the expected sensor value for each of my sensor and each of my cell of the room. And so if my sensor give me a certain value k there, we just have to address the Gaussian to get the likelihood, the wanted likelihood probability of kj, knowing s equal to si, which is in the hardware, which is done like this. So my sensor kj will register a certain value, and I have a model. So there, just the acoustic model, given by the physics law, and I compare the sensor value by the I compare it to the model, and I address it to my Gaussian. Here, my Gaussian is a semi-Gaussian centered. That's why I have to do the absolute value there. And so this will give me the likelihood that I want, and I register in each of my cell of the matrix of multiplication. Now we can see that I may have a lot of multiplication to do, n times m, which can be really high, and so that's why the stochastic computing representation might be a good solution to process all the multiplication. So the stochastic computing is another way to represent the number. Here, the number are not coded like the as in binary, but they are coded by the rate of the bits at 1 in a certain bit stream. So here you can see that I coded the value 3 divided by 8, and here the value 5 divided by 8, because I have a 5 1 in 8 bit. And so, as you can see, this representation has the advantage to reduce the multiplication by at a simple AND gate if my two bit stream there in input are uncorrelated. So it has the advantages to reduce widely the area and the power consumption, and also to be robust to bit flips if my bit stream is large enough. At a cost of a longer computation time and a lesser accuracy. But in certain case, it is not that important. Okay, so how do we generate this bit stream? We can use the a certain we can use a RNG, so a random number generator, and my RNG will give me a random number that I compare to the likelihood to be encoded. There it's 200, and if my RNG give me first 1, I will have in output 1, because 200 is wider than 1, etc. But at the end, it gave me 212, so it will give me a 0 at the end. And so this is how we code the bit stream. Since it take in input a random number, my bitstream will at the end code a good approximation of what I want to encode as a likelihood, and to convert it back to a base 2, to binary. I just have to count the number of 1 in my stochastic bitstream there, and I count the number of cycle in all the system, and I just have to divide one by the other to get the real probability. So now in each cell of my matrix, I just have to implement a comparator and an AND gate. And the RNG there can be shared on each column, since each of my line are independent. So this is the architecture of the stochastic computation core now, with my likelihoods there generated by the Gaussian, as I said, and there my prior, and now the multiplication are done with the AND gates, and I just have to get the counter at the end to get the wanted distribution. So this is exactly the same architecture, but now I just put the RNG there. And this is the base where I started my PhD. This is the base of this is where the base architecture where I started my PhD. And I just by adding some optimization, like the implementation of another way to generate the bitstream. I said there the probability circuit converter before it was a comparator. Now, if we use a weighted binary generator, which we can see that it has a part there, the first part, the weight generator, that is completely independent of the likelihood there to be encoded. So we can factorize it as the RNG. We can factorize it on a column. And so for each of my cell, I just have to implement just the second part of the weighted binary generator, the probability encoder, which is less, which is smaller than a comparator. So it can enable us to save in power and in area consumption. Another way to reduce the area and power consumption is to reuse the random number on each column, like this. I just wrote a paper on it in design and test. I won't add more detail on it. It's just to say it. And a third way to optimize this stochastic computing is to do a multi-rail multiplication there for each line, which can enable us to compute less, which can divide the number, sorry, the time of computation by 2, and thus save in energy. So as a conclusion, we can say that the sensor fusion can save energy by synthesizing the data in only one pertinent information to send to the cloud. So it computes near to the sensor, like this. And the Bayesian inference can be interesting for this kind of sensor fusion, in that it gives an explainable models, which are different from the neuronal network which has a black box effects. Like we don't know really what we are doing. There we really know what we are doing by using distribution probabilities. It can also overcome the imprecision of the data like this. And as I said, the stochastic computing can save area and power consumption by reducing all this multiplication by n gates, and can also be interesting as it is robust to bit flips. So we can reduce widely the energy the energy by reducing the VDD. And some optimization as I did during my PhD, like the implementation of the SRI, reduced up to 10% of the circuit area and 70% of the energy consumption of the whole circuit. So thank you for your attention.